So this set of videos is going to be about direction fields and equilibrium values, and those are just two different tools that we use to try to understand the behavior of solutions to a differential equation without actually finding those solutions. And we're going to start off by talking about the definition of a direction field. So, a direction field is a plot or a figure in the XY plane, just a normal kind of graph that demonstrates the behavior of solutions to some ODE given by dy dx equal to f of xy. So it's going to be a graph that shows us how solutions of a differential equation behave, and we can only do it for first order differential equations where we have just the derivative of our dependent variable is a function of that variable and the independent variable. And what the direction field looks like is, so the direction field is made of tiny arrows at every point in the XY plane. So you would call those points some x0, y0. And everywhere we look at the field, everywhere we have a point x0, y0, that tiny arrow is going to have slope f of x0, y0. So it's going to have the slope that depends on the function in your differential equation. What this does is these arrows are going to indicate the direction of a solution to the differential equation at any point x0, y0 where we look at the direction field. And eventually what we'll do is we'll use those arrows and we'll kind of follow the direction they go to see where the solutions go. And it's really hard to understand that in words, so we're going to draw an example. So the example is going to be for the differential equation dy dx is equal to 0.2 xy. And so in this case, the f of xy that's going to be equal to dy dx is just that 0.2 xy. And the direction field means that we're just going to ask ourselves, what is 0.2 xy at every point? What slope does that give an arrow in the direction field? So I'm going to sketch out the start of the direction field right here. It's going to live in the xy plane. And I'm going to break it up into a bunch of cases. X less than 0, y greater than 0, and x equals 0 or y equals 0. So when we're thinking about the product of two numbers, sort of the sign of it is going to change depending on the sign of the two numbers that we're multiplying together. And since I'm drawing a bunch of slopes, I'm going to care if those slopes are positive or negative. So I went ahead and I broke this down by case where the two numbers are positive, the two numbers are negative, so on and so forth. And so in each of these cases, we're just going to ask ourselves, what is 0.2 xy? And so for this first case where x and y are positive, when I multiply two positive numbers together, I'm going to get something that's positive. Similarly, when x and y are both negative, if I multiply them together, I'm going to still get a product that's positive. If they have opposite signs, x is bigger than 0 and y is less than 0, or the opposite, x less than 0, y bigger than 0, I'm going to get a negative product from them because their signs don't match. And then in the case where either x is 0 or y is 0, when I multiply the two variables together, I'm going to get that their product is 0. And so in all these different cases, I care about what is f of x, y, what kind of slope does that give us. So when 0.2xy is greater than 0, that's a positive slope. Oops, that's where I wrote the outline for you all. Or something that points upwards. And then when 0.2xy is less than 0, like here, that's going to give me a negative slope. That's something that points downwards. And then over here, when I have 0.2xy equals 0, that's going to give me flat things. The slope is 0. That's something that points horizontal. And so what I'd like to do is populate this whole graph right here with arrows that have slopes that match 0.2xy. And so I'm going to make kind of a lighter picture of just the overall rule, and then we'll break it down into the smaller parts. So I said that when they both have the same sign, if they're both positive, I'm going to have things that have positive slope. And when they're both negative, I'll have things that have positive slope. And then when they're opposites, I'll have things that give me negative slope. And then along the axes, I'm going to have horizontal slopes. Because like along this axis right here, y can take on any value, but x is 0, so 0.2xy is 0. And along the x-axis, the opposite happens. No matter what x is, y is 0, so I get a 0 slope. And then one thing that I want to note about this is that the slope, which is sort of like the magnitude of 0.2xy, is going to increase with magnitude of xy. So the slope becomes like technically smaller in these regions where it's negative, but if x and y take on bigger values like negative 1,000, you're going to have steeper arrows. The magnitude of that slope is larger. And then that's just going to give us the overall rule that slope is going to kind of start from 0 when x and y are equal to 0. And then that slope is going to get larger with the magnitude of x and y, or it's going to get steeper the further you are from the axes. And so what that's going to mean is that I do have these horizontal, I guess you'll be able to see this in color, so I could make it like red arrows maybe. Yeah, that'll be nice. Okay, so we're going to start with these horizontal slopes. 0.2xy is 0. Everywhere I've drawn a little red arrow. And then as you move away from the axis, the slope is going to start to take on values, but they're still going to be pretty small if you're close to the axis. So up here I know that I'm supposed to have positive slope, but maybe it's only ticked up just a little bit when I start to increase away from the axis, but this points further, so it points up even more. And this points even further, so it points up, let me try to make that more dramatic, even more. And if you imagine I care about the solution everywhere, for every x0, y0, I would fill in a bunch of tiny arrows. And I'm going to do that a little bit sloppily, just to give you the overall idea of what that would look like. So just roughly, I'm trying to make arrows that point more steeply the further they get from the origin. And then the kind of same thing is going to happen for positive slopes in this quadrant down here. The least steep ones will be closer, oh, that one's a little too steep, closer to the origin, and then the most steep ones are going to be really far away, and then they'll kind of smoothly make that change. And if you were better at drawing than me, that would be true of every arrow. Just trust me that that's the shape they're supposed to have. And then in these two quadrants that we haven't done yet, that's where we have the negative slopes. So we're going to want them to start pretty close to 0 down here, be very steep but negative far away from the origin, and then just kind of try to smooth that out a little bit. And then same idea in this last quadrant. I have something that is pretty shallow but pointing downwards close to the origin, something that is very steeply pointing downwards away from the origin, and then a kind of smooth transition between them. So that is what a direction field looks like. This thing that I've created right here is a direction field, and the general idea of how we make one from a given differential equation. I'm going to go ahead and pause real quick right here, and then next we'll go on to talking about, how to use direction fields.